Do you all ride bicycles? As you turn the bicycle, do you actually bank your body? Or you actually, when you turn the bicycle, you just turn it like that? You know you're going to fall. Some of you rollerblade. Am I right? When you rollerblade, when you turn around the bank, you will bank yourself. Am I right? You go to East Coast. You have a displacement. Everything starts from displacement. Is it a vector or a scalar? Vector. Why?
Direction.
It has a direction. From what, Caleb? From what? When you have a direction, you must have something. Or a reference point. Reference point. So, if I were to draw it fundamentally, this is the reference point. And if this is...
First law. What is Newton's first law? Can you recall? Louder? Nisha, can you say it louder so that everybody else can hear? Don't be shy, you know the rest. Okay. An object in motion continues in motion. Alright, now I have a question for you. How can an object be moving at a constant speed and still have net acceleration? Okay? Before you even answer this question, I want you to consider this another question. A very typical O-level question. Okay? Example. A woman. Okay? A woman is walking at a constant speed in a straight line at 5 meters per second. In the same direction. Okay? I have another O-level question. What is the constant velocity of a woman? Okay, a woman walking at a constant velocity of 5 meters per second. What is her net acceleration? 0 as well. Now, why is it again? Why is it 0 again?
Energy, you are damn good, seriously. Okay, you are very good. Okay, but when the ball, okay, if you just hear all the energy is being converted to kinetic energy, the ball is very energetic. Then as it goes all the way to the top, what happens again? When all the kinetic energy is being converted back to gravitational potential energy. Okay, we are going to assume that this is an ideal case. Okay, that the conversion is 100% perfect. The demonstration that I showed you all is not perfect because there's energy loss. Okay, but for ideal case, this is what's going to happen. Okay, there is one thing that I need you all to take note of. Kinetic energy of 0. What will its velocity be? It has to be also 0. Here, the velocity must be greater than 0. And here, the velocity must be 0. Okay, because basically, if something has no kinetic energy, for example, I put it here, no kinetic energy, it cannot be moving. Okay, so now this is the important part. You all have learned circular motion concepts, right? And now we have revised conservation of energy concepts. We are going to combine the two to understand why when at this point the thing will fall down. For an object to be in circular motion, what must one condition be? What must you have? You're answering too much, you can ask another question. Okay. This object is rotating at angular velocity, and the radius r on the center of rotation. And if this is the linear velocity, do you recall the expression for this topic? E is r. Anybody want to make a meaning of this? What is the meaning of what do you understand by uniform circular motion? What is constant? Yes, the motion is constant, but which of these physical quantity is a constant? Yes, that's good, the velocity, but in physics, what you say must make sense. Whether it's going to be linear velocity, whether it's going to be angular velocity. So, it's going to be angular velocity. Uniform circular motion, omega must be a constant. So at least you got that. Omega is a constant. Now,
we have, Mr. Khan has already summarized the four important equations that you need to know. V equals to R omega. Omega equals to 2 pi over T or 2 pi f. Okay? Your centripetal acceleration and centripetal force. Now, what I'm going to do is basically looking at applications of circular motion. Alright? Okay, it moves in this manner. Alright? Now, before I even go into circular motion, alright, you must know that actually circular motion is just an extension of Newton's laws. Do you know that? You actually know that? So, before we even talk about circular motion, alright, I want you to tell me, what are Newton's laws? Alright, I'll focus on only the first two laws because it's more relevant to circular motion. So, one, can you tell me what is Newton's first law of motion? First law, are you sure? That's the second law, alright? That's the second law, which is F equals to ma. Alright, I will talk about this later. I want you to tell me first law first. Must always go from first, second, and third, right? The what? The forces acting on the object is equal. Is that right? Okay, so any comments? Okay, can you tell me an answer? An object in motion. Yes. Continuous. Continuous until when? Forever. Unless the resultant force acts on it. Okay, so an object in motion continues in its state of motion. Okay, state of motion. Okay, or an object at rest. Okay, stays in its state of rest unless acted on. Okay, by a resultant force. Okay, then what about Newton's second law? What's the difference? F equals to ma. Now, when you talk about F equals to ma, what is this N you're talking about? Resultant force. Okay, so net and resultant force are the same one. So I just use a shorter one. Okay, net force is equals to the mass times the net acceleration. Now, can you tell me examples of examples that show first law? A very simple one. R? Or car. What do you mean by car? The car moves from rest. So is there a net force? Now first, can you tell me what is the direction of your velocity? Let's say it's moving anti-clockwise. Ready? What's the direction of the velocity of the car? Where? For this part? This part? This part, which direction? Like that. Anti-clockwise, yes, like that. Okay. Everybody agrees with Bernice? So that means this way, for this part, it's also like that, is it? So which direction is it? Down. Okay, why? It follows, what does it follow? This velocity. It follows what? Remember, I told you it will change my magnitude of the velocity. So that's why I have a net force this way. But then what's my net acceleration? What's the direction? What does it follow? Direction follows your second law of motion. So that means my net force is red color is for net acceleration. Okay. So it follows this. Alright? Now, I did not even for once mention centripetal force. So, what is centripetal force? The net force. Okay, is it a new force? It's not not a new force. So that means there is a force that is contributing to this net force. Now for this car, can you tell me what is the force that contributes such that it moves in this circular manner? Okay? Now what can you look at when you do this? What must you look at? Okay? I have a car here. Now this is top view, right? So